let's look at today's challenge problem. So problem 1695, maximum erasure value. So this problem actually is similar to problem 1658. So here we are going to provide a solution using the standard two-pointer sliding window method again. So first we will walk through the statement of the problem. Then we will analyze the main idea for the solution. Lastly, we give the code and digest on several of the examples. So the problem asked that for a given array of positive integers called nums, and we would like to erase a subarray containing unique elements. So the score we get by erasing the subarray is equal to the sum of its element. So the return is the maximum score we can get by erasing exactly one subarray. So here again we are considering subarray, not subsequence. So let's look at the constraint. So here the num is not empty because its length is greater or equal than 1, and its length also can be up to 10 to the power 5th, which means that we should avoid to using pure brute force. So the second constraint is about the range of elements in the nums. So now let's look at the main idea for this solution. So as we have practiced quite a number of problems using the two-pointer sliding window method, here actually the main idea should be much routine for us. So the method we're going to use is the two-pointer sliding window method. And here the condition is that the subarray that we are going to erase contains unique elements. So then, but the return is not the constraint. So it's actually return the sum of the corresponding subarray. So here the main point is how to check uniqueness of elements in the potential subarray. So that's the problem. So here again in this problem, the main idea is for each index, let's call it I. So we can also regard this I as a right boundary. So we find the longest subarray with unique elements ending at I, right? So then if for each index we can find the corresponding subarray satisfy the condition of the problem, then we just compute the sum. Then we return the maximum of the sums. So in order to incorporate this, we just need to track the partial sum in the linear scan. So with that said, let's look at one example. Let's look at this example. For this example, for example, for index I, when the subarray ending at 0 and with unique element is 4, right? Its sum is 4. For I equals 1, so the longest subarray ending at this index and with unique elements is 4, 2, and its sum is 6. For I equals 2, such array is 4, 2, and 4, because the first 4 cannot be included due to repetition. So the sum is also 6. And for I equals 3, the such subarray is 2, 4, 5, which has sum 11 for I equals 4. So the corresponding subarray is 2, 4, 5, 6. So the sum is 17. So this is 6 plus 5, 11. 11 plus 6 is 16. So the maximal sum among this is 17. So we return 17. That's basically about the problem and the main method and idea we're going to use to solve this problem. So this is a standard two-pointer sliding window method. So in order to check the uniqueness, we're going to refer to a set. Let's call this set a window. Let's call it initialize this set. And also we want to initialize a variable called result, which is the result we are going to return. The result is the score. So also we need to maintain a partial sum originally set as 0. So then we set the start of the left pointer. Then we can, for each of the right pointer, we find the corresponding longest subarray with unique elements. Then we compare the sum in the process. So this is rather routine. So for IY in enumerate nums. So then each time we are doing check and update again. So first step, check. So the partial sum, when we look at the index I element, is incremented by this value, right? Corresponding value. Partial sum is incremented by Y. Then we want to check if there are subarrays ending at index I and with unique elements, and what's the maximal score we can have. So we can do a while loop while Y in this window, right? It means it already appeared before. So we need to pop until Y just as Y was popped out. So then we can track the partial sum in between. The partial sum is decremented by the nums L. The effect of this partial sum decrement is corresponding to we delete or remove this number L in the window. So once we done this, so we push the left pointer to right by 1 unit. So once we exit this while loop, then we know that we have one subarray, longest subarray, ending at index I, and with the sum being the partial sum. Now we just update the result. The result is maximum result and the partial sum. So this is the check step. Now we need to update the window. So if Y is not in the window or is in the window, actually we also popped it in the check step. So we need to window, we add this current element in it. So once we done this, we are ready to return the result. So let's return the result. First, let me check several simple cases, and then I will print some information to gain a better understanding about the method. So let's see here. This passed this case, and then let's try this test case. So we get this one that also passed. Let's look at the generic case. It passes. So now, in order to have a better understanding, actually we can print out the result and the corresponding longest subarray with unique element at each index. So let's print this one at index I, and the array is basically this array nums from L to the current I, so it's I plus 1. So let's check this for this one. So for example, for this one, ending at index 0, the corresponding longest subarray with unique element is 5. Similarly, at index 1 is 5, 2, and the index 2 is 5, 2, 1. At index 3, we can only have 1, 2. We cannot move left because of repetition. So this is basically the recap of the main method. That is, for each index I, we find the longest subarray with unique element ending at I. So the better feature for this problem is that in the process, we can do all this in a linear fashion. So that's about it. Thank you.